Good, thank you. I appreciate it. Anyways, I'm going to welcome you to a new season of seminars in the Create for STEM. I believe it's our 13th season coming up, which is pretty great. So I'm really pleased about that. And I'm pleased to see that we have a crowd here. And I know there are some people also on Zoom. At least they told me they were going to be on Zoom because they said they couldn't come. So I'm really pleased that you guys are here. And we got a nice crowd. We have more people flowing in, so I'm really pleased. And I'm really honored to introduce our guest speaker today, David Fortus from the Weissman Institute of Science. Some of you may recall that David is actually a former faculty member here at Michigan State University from 21 years ago. I wouldn't have got that number right, but it was a fairly long time ago. So I'm really pleased that David is here and is going to spend some time talking to us about some of his recent research in teaching science. David, welcome.
Thank you very much. Can you hear me? My voice clearly? Oh, it's always a pleasure to come back to Michigan State. It's nice because things don't change so quickly, and so I still see my room where I used to sit, same layout, same people. It's nice. I feel very much at home very quickly at Michigan State. What I want to talk about today are some of the theoretical ideas, and it's not just theoretical, there's a lot of empirical data here also, that underlie a large NSF grant that I received together with Troy Sadler from the University of North Carolina at Chapel Hill. And the project is called, we have here, the Grand Challenges. To put very simply, the goal of the Grand Challenges is to change the way science is taught in schools. Big goal, okay? When we applied for this, we laid out a 15-year plan. And we asked for money for the first 4 years. To get it started. The answer is yes. Now, what it will be next step and so on, I don't know. So I'm not going to describe the entire project, okay? But the project, its justification is based on some of the ideas that I'm going to present over here. Okay, so that's the framing we want to do right now. Much of what I'm going to say has been published already in 2 papers. One was published a year and a half ago. The first one, again, this is Troy Sadler. Knut Neumann, he's in the room just around the corner. He happens to be here right now also, visiting. And Jing Lin, she's from China, from Beijing Normal University. This was on purpose an international paper because we want to show that our claims are relevant to very different countries around the world. So it's very much interesting, and that's why it's published in the International Journal also of Science Education. The second one it's a paper that's been resubmitted, and it's about restructuring the science curriculum Grand Challenges. Again, it's with Troy Sadler, and Jen, she was a postdoc of Troy's. So if you want more information about what I talk about, these are the 2 places where you'll be able to get more detailed information about. Now, one of the goals of the project, or actually the main goal of the project, is to help kids develop what we call informed agency. Okay? A lot of people can feel agentic, but not know what they're talking about. Okay? Some people can know what they're talking about, but don't have this need to try and make a change in their lives and the world and so on. We want to put them together. We call this informed agency. And so there's an affective component and a knowledge component combined together. And when we talk about affect, we talk primarily about 3 aspects of affect. One is self-efficacy, the other one is mastery orientation, and the third are positive attitudes. Okay? So, what are the Grand Challenges? Grand Challenges are global socio-scientific issues that have varying local implications. So they are present everywhere in the world, but the way they manifest themselves changes from one place to another. These were the big issues that are shaping our lives, and they will continue doing so, at least that we will continue doing so for at least 20 years. Down the line, though, as time goes by, of course, new grand challenges will enter and other ones will leave. And again, we on purpose chose big global ones because this is an international project. Right now it's between the United States and Israel, but already Holland is getting on board with Germany and China. And the idea is that this is something that everybody should be thinking about, not just a local issue. And so it's just some examples of these grand challenges are climate change, personalized medicine, pandemics, availability of fresh water, and so on and so on. Now, we include also inside here not just issues that are problematic, that are threatening, but we also sometimes include issues which are topics of wonderment. So for instance, living on Mars is an issue that we're facing today. Why should we feel everybody should learn science? And traditionally, there are 5 arguments that are given for this. Now, some people have been 9 arguments, 7 arguments, 3 arguments. It depends who you read. But I think these 5 arguments distill the main ideas very well, and I'm going to draw upon them again and again throughout this talk. They were all appeared in a paper by Robin Millar, published in 1996. And there are 5 top arguments: the economic one, the utilitarian one, democratic, social, and cultural. And just to show that these things, a lot of people are thinking about them, let's take a look at the opening paragraph from the framework. The opening paragraph. And I'm going to read it to you. The overarching goal of our framework for K-12 science education is to ensure that by the end of 12th grade, all students have some appreciation of the beauty and wonder of science. That's a cultural argument. Possess sufficient knowledge of science and engineering to engage in public discussions on related issues. That's a democratic argument. Are careful consumers of scientific and technological information related to their everyday lives. That's a utilitarian argument. Okay? Are able to continue to learn about science outside of school, a lifelong learning argument, and have the skills to enter careers of their choice, including but not limited to careers in science, engineering, and technology, and economic arguments. So what Robin wrote back in 1990 something, okay, it's there inside the framework. And we looked at conceptual or standard documents, as I said, in many other countries, and these ideas reappear all the time. Let's start from the economic argument. I want to read it to you as Robin wrote it. There is a connection between the level of public understanding of science and the nation's economic wealth. In addition, scientific and technical achievement is seen as a sign of a nation's international standing. Maintaining this depends on a steady supply of technically and scientifically qualified personnel. We decided to see if this is indeed true. So we needed a measure of a country's wealth versus a country's knowledge of science. What we choose is a proxy for knowledge of science, or PISA scores. Now, clearly this is not the measure, but it's a national measure of people who are going to become citizens at some time. And we took all the data we could find. We eliminated 3 outliers over here, which were Qatar, Norway, and Liechtenstein. Why were they eliminated? Extremely high GDP. Okay, but that's not a reason to exclude them just because they have high GDP. The thing that Qatar and Norway are very, very rich countries simply because of national resources. That's it. Okay, selling gas and petroleum. Okay, very, very well. Norway was one of the poorest countries in Europe until they discovered natural gas there. Okay, their main industry was sardining. Okay, catching sardines. Qatar is completely built upon its wealth of petroleum, so knowledge is driving there. Liechtenstein is a tax haven. Okay, it's a small town in the middle of Europe that all the wealthy people in Europe live there because they don't pay taxes or they pay less taxes, and so it's a very, very wealthy country, but they do nothing. So those 3 were excluded. What's important is you can see that there is a general positive trend, okay, that a linear line explains about 32% of the variance, which is in social sciences, that's something significant. So yes, there is a combination between a nation's wealth and a nation's knowledge of science. But the question is that does not give you causality. It doesn't tell you whether it's the knowledge which is driving the wealth or the wealth which is driving the knowledge. In other words, simply wealthier countries invest more in education and therefore their kids do better on the exam. So we went further. And it turns out that this has been studied by two German economists who focus on the economics of education, named Hanuschek and Wösmann, in a book that's called The Knowledge Capital of Nations. And basically what they did, they controlled for countries' initial GDP, and they looked how this GDP grew over time dependent upon the knowledge of the kids, of the people in the nation. So they basically answered the question that I looked at before. And what they found is two things. A 10% increase in all students' knowledge of mathematics and science predicted an increase in the annual GDP of 3%. Okay, of 0.3%, while a 10% increase of the top performing students predicted an annual 1.3% increase in GDP. So the top scoring students, by focusing on their scores, it has 4 times the effect as is working on everybody. Okay? Now, so we ask ourselves, why is it that the top scoring students predict growth in GDP so much more? And our assumption was that because top scoring students are the ones who go into science and engineering, and they're the ones who build the capital of the country. So we said, if this is true, there should be a relationship between the number of scientists and engineers and the wealth of a nation. So we looked at that one, and that's the next graph. Here we have the number of scientists and engineers per million people, and here we have the GDP, and the line is stronger than before. It predicts 70% of the variance. So it's very clear that the main driver of countries' wealth are the scientists and engineers. Now, when we put that together with what we saw beforehand, okay, it means that the goal, the economic goal of science education is to increase the number of future scientists and engineers, because they're the ones who generate the economic wealth of a country. Okay? If that is the conclusion that we reach here, the question then is it important to continue teaching science to all students even after they choose not to go into science or engineering? So for instance, until middle school, everybody says everything. Okay, but at a certain stage you start making choices. And kids in high school, at least studies show that by the age of 14, 15, most kids already know what they don't want to do. Okay, what's clear? And science for most kids is already out by the time they're 14. Okay, it's a great study done in England by a British sociologist, David, and I don't remember. Anyways, so why continue teaching science to those who have chosen not to become scientists? Because they're not going to contribute to the economic wealth. I'm talking about economic reasons here right now. Okay? It's not clear what the answer is. So, our next question then is, okay, so in this case, what predicts whether students will go into STEM at all? And it turns out that grades in science are poor predictors. Okay? The strongest predictor that we know of is self-efficacy, belief in your ability to work in that field, and your enjoyment of your science studies. And that is based upon 2 studies done based on PISA data. PISA looks not only at knowledge, but it also looks at attitudes and about all kinds of things. And so, summarizing everything that we said right now, the economic goal of science education is A, to enhance students' self-efficacy and enjoyment of science studies, thereby increasing the number of students who choose science-related professions. That's number 1. The second one is to improve the knowledge of the top scorers. Okay, now, so this goes against a lot of the stuff that I was brought up on Science for All. Okay, that you provide. Okay, it does not fit, but again, you have to remember we're talking only about the economic perspective. There are other perspectives. But on the other hand, it does help me understand some of the policies that I see some countries sometimes making regarding science education, because policymakers are typically very much driven by economic considerations. And so it makes more sense sometimes when I see certain decisions being made. Any quick questions? Okay, we're moving on to the utilitarian argument. Again, I'm reading what Robin Law wrote. An understanding of science and technology is practically useful, especially to anyone living in a scientifically and technologically sophisticated society. They are better equipped to make decisions about diet, health, safety, and so on, to evaluate manufacturers' claims, and to make sensible consumer choices. So, we address this argument in two ways. The first one is the way in which digital technologies have influenced the need for science knowledge to navigate life in the 21st century. The second is the role of knowledge in decision making. When we look at the first one, we came upon an article by Chapman written back in the 90s called The Overselling of Science Education in the 80s. And a lot of the things that we're saying now, he already saw them there, but they've just become a lot stronger. Way back when, okay, in order to make things work, you had to understand how they work. People used to tinker with their cars. I remember as a kid taking apart a record player to see it and figuring out how to say, okay, ham radios, okay? So you had to understand the science. Today, everything is a black box. Everything is idiot-proof, designed so that anybody can use it without knowing anything. And I love this t-shirt. I'm an engineer, I make things idiot-proof, but they keep on making better and better idiots. So what has happened is that actually the introduction of digital technologies into everything, okay, has decreased the need for STEM knowledge in everyday life. Because things are built up so you won't need any kind of knowledge. When is knowledge still sometimes useful? Sometimes it's when things don't work the way they were supposed to. And then you have to start figuring out what's going on. But we'll see that even there, it's not what we think. So, for example, STEM professionals such as technicians and mechanics, even they barely need scientific knowledge. Why? Okay, you have an air conditioning problem. You call up an air conditioner technician. What does he come? He comes in, he takes out this unit, he plugs it in, he runs a self-diagnostic test. It tells him this part is wrong. He does under the screws, he takes it out, he replaces it with a different one. That's the end of it. He doesn't understand anything. This is true about cars. Every modern day car comes with a standard plug that you go to a garage, they plug something in, it runs a diagnostic test, okay, 95% of the time it tells them what's wrong. So even when things are wrong, you still don't need the STEM knowledge. Okay, what do these people use? Okay, they use practical knowledge. It's not scientific knowledge. There's no theory underlying it. Okay? On the other hand, people who design these technologies, they still need scientific knowledge. That's still there. But even there is disappearing. Okay? I studied engineering. Okay, today. Okay, so the CAD/CAM programs. Okay, forget it. You put in the constraints what you want to do it, and it designs it for you. With AI now, adding a layer inside it, even in these fields, okay, the need for scientific knowledge is just increasing. But I'm saying, now let's look at it a different way. Let's say you assume you have a scientific knowledge. Let's take a physicist. Here across the road, we have a Department of Physics. When their car goes wrong, let's say it's an old 1970s Chevy, no digital technology. Does it go wrong? Will they be able to figure out what's wrong with it? The chances are that no. Theoretical knowledge does not give you the ability, okay, to make existential changes in the world. There's an additional skill that's needed inside there. There's a gap between theoretical knowledge and knowledge knowing how to put that into practice. So again, just developing STEM knowledge does not seem to help people at least make better choices and do all kinds of things in everyday life. before I go there. How many people here are vegetarians or vegans? No? Good? Okay, it's good for the next, this is good for the next slide. Okay, I want to show what happens when you have knowledge, but you don't use it. Okay? Here's something from the Food and Agriculture Organization of the United Nations. So the first is from a UN document. Okay? The livestock sector is globally one of the largest sources of greenhouse gases and one of the leading causal factors in the loss of biodiversity. While in developed and emerging countries, it is perhaps the leading source of water pollution. Okay, so livestock is bad. Okay, that's what we're saying. On the other hand, we have to eat something. Okay, so the next sentence comes from the American Dietetic Association. Okay, they wrote, appropriately planned vegetarian diets, including total vegetarian or vegan diets, are healthful, nutritionally adequate, and may provide health benefits in the prevention and treatment of certain diseases. And this is not an individual paper, this is a position paper of the association. Okay, so what they're saying is that vegetarian and vegan food is not only that it's fine, it's probably better, okay, than a meat-based diet. That's what they're saying. How many of you are vegetarian or vegans? I'm assuming that you're all as scientific literate as we can expect, okay, typical people in society. Yet, you have chosen still to eat meat. I'm not trying to criticize you. I eat also, okay? So I'm not trying to criticize it. I'm just showing here that there's a gap between what we know and the way we choose to behave, which reminded me of a phrase that Mark Twain wrote. He said, a person who doesn't read has no advantage over a person who can't read, okay? A person who doesn't use their knowledge doesn't have an apparent advantage over a person who doesn't have the knowledge if they don't use it. So we're in the same situation here. I saw you raise your hand. One second. Okay? Now, why do we behave like this? It's because we are often more instinctive than rational in our behavior, okay? People eat meat, drive big cars, and do other unwise things because these behaviors bring them pleasure, okay? It creates a sense of gratification. We're not driven only by our prefrontal cortex, okay? And then the other high is people often don't behave wisely because that involves too much effort or cost. It's harder to do things, to recycle. You have to separate things and so on, okay? You may think, that's nothing, but it's more work than not recycling. And so on and so on, okay? So it's not surprisingly that we don't always behave rationally. But that doesn't mean that our knowledge does not affect our behavior. It does. It just, its influence is often a lot less than the hype. So, okay, and what this means for me, well, summing this up to this point, is that we should be modest when we use the utilitarian argument to justify science literacy for all. It's not that it does not play a role, it just plays a lot smaller role than we tend to think. No?
I was just going to make the point that I understand your argument,
Yeah.
but I was just going to make the point that there's a range of behavior rather than on and off.
Of course.
So that eating, like I'm not a vegetarian for instance, but I eat almost all plants, I eat mostly plants. And the reason is because of the first point, but it doesn't, I don't do it, it's not a yes or no choice.
Of course, okay. So I'm saying it does influence your behavior, okay? But it's not that this is the prime driver, necessarily. Absolutely, and it changes between one person and another, how much self-control, how do you call it, self-regulation we have and so on. Yes?
Thank you.
Oh, hi.
Hi, so, my question is that, I think that the utilitarian argument on the basis of diet is probably not the strongest of the utilitarian arguments to be made, especially today. Because the utilitarian argument, I'm thinking from a sociological perspective, some, you won't be able to live and actually function without others. So I think, I would argue that maybe in 2009 or in 2000, the argument was about, the issues of food. But if we look today with bacteria and medical problems, and technological issues that we're being faced with, that I suspect that utilitarian argument will have a much bigger increase on your regression line, especially if you look at other kinds of things that are occurring in job markets, especially around technology and entrepreneurial activity. Because even in places where, in Africa and other places that we have a lot more resources being put into things that I would argue are functional in terms of choice, but in ones that are not choice functional, but actually are utilitarian and create survival or not.
Okay, I'm not sure I want to go down that, okay? What I will do, I will pick up one thing that you said, okay?
Oh, sure.
Okay,
That
no,
was a comment.
okay, okay. You mentioned modern day challenges, okay, and you mentioned health issues and so let's go in that direction, and I can perhaps come back to the rest of the argument afterwards.
Okay, yeah.
I'm just thinking how to move it in. This is just a side note. I want to show effect of how do you call it? Another cool thing, the relationship between wealth and public behavior. So this is the wealth of countries, okay? EPI is a standard measure used to measure a country's environmental behavior. Well, okay, how much their energy is from green sources, recycling, all kinds of things. Okay, it's a standard measure that used across the world. And the amazing thing is that when you plot all the countries that I was able to find data, the regression line is 0. So there is absolutely no connection between wealth and public behavior on things that we understand that should be done. Anyways, this is to go in the direction that Barbara mentioned. Another continuation of the utilitarian argument. Okay? Lots of researchers show that for people to be able to use their knowledge in given situations, the knowledge needs to be detailed and specific to that situation. When you expect people to transfer knowledge from one situation to another, it's much less likely to happen. So it's important to have information in the context in which it's going to be used and that the knowledge is detailed. So let's look at the idea of vaccinations. We just went through COVID. In order to understand a person to make a decision, a rational decision, whether they get vaccinated or not, what do they need to know? They need to know the characteristics of the pathogen and the disease it causes. Okay? They need to know how the disease can be treated. They need to know the odds of being exposed to the pathogen. They need to know how the vaccination works. They need to know issues related to weakened immune systems. They need to know the risks involved in getting vaccinated. They need to know the schedule. Why do you have to take it multiple times? And so on and so on. Okay? You have to know a lot in order to really reach a well-based decision, whether they get vaccinated or not. And this is for every type of vaccine, okay, if you have to make a decision. Now, most of this is never taught in schools. Okay, so how do we expect people to be able to make well-based decisions if they're not being taught? The only way they can do that is if they learn it themselves. Let's take a look at another example, okay? Okay, about an electric car. You're going to buy a new car, you want to know if you want to buy an electric car or a turbo-charged diesel car. I use that one on purpose because with today's technology, that is the cleanest type of car available. Okay, and not electric cars. The study came out of Stanford a while back that electric cars are cleaner than these only if at least 60-something% of the electricity they use comes from green sources. As long as you're still burning coal, okay, or fossil fuels or something, you've achieved nothing. They're less efficient. because the energy has to be transferred from the power plant to the car, and there's huge losses on the way, and so on and so on. Afterwards, in a second, okay? So, you want to make a decision what kind of car to buy. You have to know whether the source of electricity that you're going to be using most of the time to recharge your car, if it's renewable or not. You have to know about the efficiency of transferring energy from the source to the car. That changes upon where you are in the United States. The grid, the quality of the grid varies in one case to another, and how far away you live from a power plant. You have to know about the contamination caused by the car's battery. People don't realize it. These lithium batteries are terrible. No one knows what to do. They just trash them. It's terrible. Basically, we're solving one problem, but by doing that, we're creating another problem. Okay, so, but that's for future generations to worry about. We need to know about the average life of a battery. How often are you going to have to replace that battery compared to the life of an engine? Okay, people, when they buy a diesel car, they don't expect to ever have to replace the engine. Okay, it's not something, with an electric car, yes, you're going to have to change the battery at some stage because they don't last that long. Okay, you have to think about charging opportunities based upon where you live and where you travel and so. So lots of stuff you have to know in order to really reach a good decision. And again, this is not taught in schools, okay? People have to be able to learn these things themselves if they really wanted to reach well-based decisions. So, to increase the odds that people will use their scientific knowledge in decision making, they need to be lifelong learners. You cannot base just upon what you're learning in school. That is not going to help you. You have to be able to go beyond that. This reminds me of a framework that Bradford and Schwartz mentioned back in '99 called Preparation for Future Learning, in which they tried to argue that the best measure of learning is not what you know, but how well it prepares you for future learning. For when you actually need the knowledge and then you have to learn new stuff, okay, how well does the basis that you have help you then learn them? Excuse me. A study, a lovely study that was done in about 10 years ago, yeah, in 2012, they showed that people, they tried to, it was a study with university students, and they gave them a problem they had to go out and learn more, and they tried to figure out what are the characteristics of the people who go out and learn what is needed to learn, they need to learn in order to answer these questions. And their conclusion was that a characteristic of being mastery-oriented. Okay? In motivation theory, there's two types. In one, it's called achievement goal theory, who, by the way, the person who started this theory and made it really famous was Carol Ames, who was the dean of the College of Ed. Okay? So according to her, this theory, there's two types of motivation, mastery-oriented and performance-oriented. Mastery-oriented people learn because they have a need to understand. Okay, an internal need, they want to have a sense of mastery. Okay? The second type of motivation is performance-oriented. These are people who learn because they want other people to think that they know. So either you learn because you want to know or because you want other people to know. Those two things. Now, all of us, we have a bit of both. It's not dichotomous. Okay? Everybody has a bit of both, but the issue is if people are not strongly mastery-oriented, they are unlikely to become lifelong learners. That was the finding of this study. Okay? Now, the odds that people, even if you're mastery-oriented, it still doesn't mean that you're going to go out and learn what you need to learn. You have to be self-efficacious about your ability to learn it all. Okay, the number one reason that people don't go on diets is because they don't believe they'll be able to maintain the diet. So why even start? Okay, it's true about everything. So if you don't believe in your ability to go out and find things that are relevant, okay, and learn them, you're not going to start. So there are two conditions that need to be met here. One is self-efficacy, and the other one is to be mastery-oriented. So, to conclude the utilitarian argument, and well, I'll speed it up a bit. First, my sense is that we have to be modest about our expectations regarding the utilitarian value of science literacy. And the second is that in order to enhance the value that it does have, okay, we need to focus not only on knowledge and skills, but also on students' tendency to be mastery-oriented and self-efficacious. For Forget it. We'll move on. You don't have
There was
to.
a question.
Yeah, there was a question over here. No? Okay. Democratic argument. I'm going to speed up. I'm going to shorten things. An understanding of science is necessary if an individual is to participate in discussion, debate, and decision-making about issues which have a scientific component. Decisions have to be made about transport, energy policy, testing of drugs and treatments, disposal of waste, and so on. There should be public accountability about the directions of some scientific research, and public involvement in decisions about whether or not to apply such knowledge. Now, this is a statement from Scientific American, the Board of Editors, again, so it's, citizens have the right to participate in discussions, debates, and decision-making about scientific issues made locally and nationally, regardless of their understanding of the topic or their social cultural beliefs. This often leads to behaviors and supports of policies that run contrary to accepted scientific knowledge. Okay? So we're not arguing about the right to be involved, okay? It's what we want people to bring to the table. A lovely study, really lovely study that was published in Nature, okay? They took people, okay? They asked them about their educational level, and they asked them if they think that mankind is responsible for global warming. I'm putting it very simply. It was worded differently and so on. And they predicted that in general, there would be a positive trend. In other words, the more you were educated, the more you understood the science, okay? The more you would say that yes, that we're responsible for climate warming. That was their prediction, okay? What they got was this. They got pretty much a flat line, but then they disaggregated the data according to which party you voted for, okay? And the prediction worked for Democrats even stronger than they predicted before, but for Republicans it went the opposite direction. The more they were educated, the more they opposed, okay, humans being the source of climate change. This is shocking. So, making people scientifically literate, teaching people science, can often have the opposite effect than you expect, that we expect. Okay? So, assuming that we are trying to promote a particular position, which I think is not true. We all are in some way trying to promote certain position. Although we say we're neutral, but when we teach about climate change, we teach about it, okay, as something that humans are causing. So we are trying to promote a certain position about it. Okay? So we need to ask, okay, ourselves, can science knowledge compete with ideological leaning? If yes, what level and what kind of science knowledge is required to be able to truly understand and influence, not just accept the position of your favorite politician? And can this level of scientific knowledge be reached in K-12 education? The thing is, I want to go back a second. One of the things they found in the study is that the more you understand, the more you're able to find fallacies in your opponent's argument. This is what they're doing. You're better at explaining away the arguments that other people are giving. Again, this is like with the utilitarian thing, the chances that people will know everything that they need to know to really be able to understand what's going on. Climate change is a very complicated, complex thing, okay? And not just accept the opinion of your favorite politician. We're not going to be able to reach that level of knowledge in K-12 education. Plus, this is our living topics, so the new things are coming up all the time, okay? Which brings us back again to the issue of lifelong learning, which brings us back to mastery orientation and self-advocacy as crucial things if we want people to be able to use their knowledge they have in real-world situations. Studies that have been done mostly in England by Jim Ryder, they show that actually knowledge about science rather than knowledge of science are of greater utility in the public domain. So understanding how science works, how scientists create their group, and so on, rather than understanding the nitty details about their actual explanations and prediction is more important. A special utility was understanding how science claims are constructed and justified. And this is the article from which I drew this. I just love this cartoon. Okay, there's all these scribbles on the wall, and in the middle, this guy has written, "Then a miracle occurs," and he says, "I think you should be a bit more explicit about this step." So the procedure is important, not just understanding the details. So to conclude the democratic argument, I think that to enhance the democratic value of science education for all, we need to focus on students' tendency to be mastery-oriented and self-efficacious. And 2, we need to emphasize knowledge about science, not just knowledge of science. That's the conclusion from this part. Social argument. It is important to maintain links between science and the wider culture. Specialization and the increasingly technical nature of modern science is seen as a social problem, leading to incipient fragmentation and the alienation of much of the public from science and technology. A related argument is advanced from the science side, that improved public understanding will lead to more sympathy with and hence greater support for science and technology itself. I argue that this is not as much an argument about knowledge as an argument about attitudes towards science. Okay? It basically says that we need to develop and strengthen positive attitudes toward the scientific enterprise, not necessarily science, knowledge, and skills. Which raises the question, can a person hold positive attitudes towards science without having strong scientific knowledge?
Yes.
Okay? I don't know the answer. I've said that my instinct is that the answer is yes. There are topics of science that I know nothing about. I don't know anything about cardiology. Okay? I have a very positive attitude towards what they do. Okay? So I'm assuming it's possible, again, that I'm a case n equals 1. I don't know the answers to this. The cultural argument. Science is a major, indeed the major achievement of our culture, and that all young people should be able to understand it and to appreciate it. We should celebrate science as a cultural product. Well, I don't exactly agree with the major, but never mind, this is what Robin goes. Okay, it definitely is an important achievement of our culture. But this argument is true not, I think, not only for science, it's true for art, music, drama, lots of other things which have changed our lives dramatically. Okay, why do we expect people to be scientifically literate and not dramatically literate? Okay, why isn't drama a required course throughout K-12 education? In ancient Greece it was. Okay, in Waldorf schools, it still is today. But again, like the social argument, this is more an argument about attitudes, less an argument about knowledge. It's not about science literacy in the typical sense. By the way, do you know what these pictures are? This is a picture of Voyager. Okay, it's no longer in the solar system. It's a satellite that they sent way out. Okay, just hoping that one day some alien would find it, and they put on it a gold-plated disc that contains information about Earth, all kinds of information. That's the goal. Okay, is to go out until hopefully someday. That's wonderful. Okay, it's great. Yes, it's great. This, do you know this line? Beethoven. Okay, Beethoven. Okay, this example of great cultural thing that people that have checked our life. We may not listen to Beethoven today, but modern music would not have existed as it does without this person. Okay, he changed music. Okay, changed the way music was done. Does anybody know what this is?
A Renaissance painting?
Pardon me?
A Renaissance painting?
It's by Raphael. It's called the Athenian School. It's in the Vatican. It's on the wall. It's painted on the wall. It's a fresco. Okay, it's not much bigger than this. It's about twice its width. It's not a big thing. It's one of the most incredible paintings ever made. Okay, why is it called the Athenian School?
It's all the famous thinkers hanging
Right.
out.
Right. Every figure here is a famous person from Greek philosophy. Okay, and he drew every person, okay, in a position and so on that he felt reflected their philosophy. So there's a guy here, okay, who's on the stairs and in rags and so on. Okay, okay. they are all talking to one another according to the way their philosophy. So you can learn about philosophy a lot by looking at this book, at this thing. Now, there's two other amazing things I think about this drawing. And first is that this is also a historical drawing. In other words, what Raphael did, he chose people who were living at that time, who he felt reflected the philosophy of that certain philosopher in their behavior. And he used them as the images. So every drawing inside here is of a person who's actually living the time of Raphael, who behaved in such a way that Raphael felt reflected that particular philosopher's philosophy. Who are the two main figures? Plato and Aristotle. Those are the two main people in the center. Okay? Plato, if you know his philosophy, he's talking about the great, the better, the great world, and he's pointing up at the sky. And Aristotle, who's the ground to earth, his hands like he's saying, hey, not so quickly, hold your horses. Okay, like that. So you can see all these kind of things. Who did he feel was Plato, the perfection, how the greatness of the world and so on? Who do we know was like that? Da Vinci. This is the only drawing of Da Vinci, not by Da Vinci. Okay? He used Da Vinci as his model. Okay? Who did he use as Aristotle? This is the only person that was not a living person then, because Aristotle was the only philosopher for which a bust existed, that there was a remnant of how he actually looked. And so he used the stone bust of Aristotle in order to make the drawing of Aristotle. So I'm just showing this that, not only science is amazing, we can go on and stuff like that, other things can also create, and I think just in these 2 minutes talking about this, I may have changed in some small way your attitude towards art. Okay, so it is possible to change the attitude. Why aren't we teaching science in such a way to actually get kids? Wow. I don't know. Anyways, last slide. I think let's summarize. What I've said up to now, the economic argument is teaching science. What are the conclusions? We need to teach science in a way that enhances enjoyment, interest, and self-efficacy in order to maximize those who will choose to major in science. And B, we need to promote understanding. It's more important to do that for the top achievers than for the general public from an economic standpoint. 2, utilitarian argument was to teach, again, to enhance mastery, orientation, and self-efficacy for autodidactic, for your ability to learn yourself. 3, the democratic argument was to teach about the epistemology of science, and again, to help enhance mastery, orientation, and self-efficacy. The social cultural arguments say to teach to develop positive attitudes. There are some things that are in blue, some things that are in black. Those that are blue uses the underpinnings for the project, the grand challenges. These are goals that we're trying to foster in the grand challenges project. Now, all the standard documents with which I am familiar ignore these conclusions. Many studies, including some of them done by me, have shown that students, their mastery orientation, attitudes, and self-efficacy decline dramatically between 3rd and 9th grade. What would a pedagogy that takes these issues into account look like? And that's the goal of the grand challenges.
We have about 8 minutes for questions. So do we have questions? Comments? And David's going to take a drink of water. Go ahead, David.
So, first of all, thank you. Second, I think the major difference between science and art in that aspect is the fact that artists can see that something that's more, it's less rigid, let's put it this way. Science has rules. Science has underlying concepts and characteristics, things that people conceive science as right or wrong. Dichotomous in that way. That something in art, for the sake of discussion, things that can be considered art or correct in the eyes of art, even if others don't agree with them. So you have all those currents in art. And you can look at Picasso's work, and you can look at people from the Renaissance, and you can look at contemporary art, and you can say, okay, all these are art, and they can be of the same object, and they will consider true to the art form. But in science, there's usually just one right answer. So this dichotomy that exists in science, looking at issues that we have today that has a political nature, and trying to diffuse them from a position of, listen, we accept to hear both sides of the story. The science is true whether we accept it or not. Art in that aspect is a bit more fluid, and maybe that's why people are more intent to accept different approaches to art, but in science it doesn't exist so much.
Taking the historical example that you use, Picasso, Rembrandt, and so on, you don't know how many artists were canceled in their time because they broke conventions. They went against what was accepted. Okay, so that's been true for art also. Okay, I think art simply has a longer history than modern science, and therefore it's richly, okay. In science also, I can give you plenty of examples. Think about Copernicus. Okay, that's probably the most famous one. I'm not arguing with you that there are rules of the game in every field, okay? And people who break the rules, okay, have to face the
Music.
and so on. It's true everywhere, so I don't think that is bottom line the reason why. What I'm trying to say, I think the reason that I heard you trying to talk about rejectionists of science people. Okay.
No, dichotomizing. The fact that when you go into a classroom and you talk about art, people are willing to accept other forms. When you talk about science, it puts people in either side of the fence.
If you talk about right or wrong, either the person's a believer or not a believer. Okay, you won't convince a non-believer to become a believer by telling them that they're wrong
About science.
about anything. When you have an argument where just telling the person you're wrong, okay, this is how it is, that's not convincing. Okay, the thing is to try, what we believe is to try and help them reach by themselves a conclusion, okay, that what I knew beforehand is problematic and I have to look for things, and here I'm offering you a different option, and so on. Why is it not true about art as well? Okay, when I learned an art and I have to make a shadow, okay, the teacher does not tell me, okay, no, that's wrong, that's not how it looks. I know it doesn't look like it the real world. If I did, I wouldn't be in this class, okay? But they start pointing out things that this may have been wrong. And slowly you build yourself an understanding of how it actually works. So I don't think the difference is that great, okay? I think we might be better off if we taught science a bit more like we teach art, okay, and help, okay? It might be better. Yeah.
Well, so following up on that discussion, what's the role of teaching the history and philosophy of science in this new curriculum?
And
What is the role of teaching history and the philosophy of science in this new curriculum? You're going to teach. When will you introduce Thomas Kuhn as an example in this curriculum?
I think if you don't know where you're coming from, you have no idea where you're going. It gives you a sense of direction. I think it's super important to teach about the history, because that's the process of justifying why we are the way we are, where we are right now. I think it's crucial. In fact, I've taught a class, okay, that was built upon the revolutions, or actually it was built about personal stories. I wanted to make it live, not just talk about ideas. So we followed people in science, okay? And it was to get a sense of, today it's not the way it was, and it's not going to be the way it used to be. It's not going to be this way in 50 years either. Now, things are changing. And I think it also, one of the reasons, it's not the only, it's definitely not the major reason, that kids reject science is their sense that it's fossilized, okay? It's this thing, this monolithic thing, it's right. Either you get it or you don't get it, okay? something like that, and understanding that science itself is dynamic. It is changing all the time, and it's changing not because it's changing on its own. These are not mutations. It's because the people who are engaged in science, okay, don't always agree with what they're hearing, and so they start pushing. Now these are small little things, but they sometimes gather momentum and convince people. And suddenly you see that something changes. So it looks static, but it's not static at all. Yeah, Bob. And then
So you've made a really interesting argument in terms of a direction here. I'm curious as to why you then chose your grand challenges as the approach to address it. Because as I look at each of the grand challenges that you proposed, they're all highly confined to the engineering and policy world. Right? So to address each of the grand challenges, right, is either an engineering task, right, or it's a policy and incentives task. And nowhere does it approach things like just the curiosity of how birds are migrating, or the engagement in abstract thinking or mathematics for the joy of that, or any of the other kind of pieces that help drive different people to taking up different aspects of science.
great question. Great questions. Great questions. Back in the very beginning.
There you go.
This is a middle school project right now, okay? It's compulsory science education. Kids don't choose. Okay? In Israel, kids after 9th grade, they can choose whether they want to study science or not. Okay, so we're doing this in middle school, which in Israel is between 7th and 9th grade. Okay, so everybody, we had to find topics which we felt, okay, had the largest ability, wise, to bring everybody in. Okay, so we wanted to have topics that would be very easy, relatively, to dramatize them. Okay, to make kids see that, wow, this is big. Most of the kids know about these topics. They've heard about them from here and there. Very few of these topics are new. Okay, but we wanted to have an emotional impact. And so in fact, each of our units is divided into 3 sections. The first section does not talk about science at all. It talks about geopolitics. It talks about economics. It shows, for instance, when we talk about water shortage, we started talking about what happened in Cape Town. I don't know if people know about this. Cape Town, about 4 years ago, they ran out of water. This is a city of 2.5 million people, a modern city. High rises, green, it's a beautiful place. If you ever go to South Africa, go to Cape Town. They have a thing called Table Mountain there. It's, oh my God, it's absolutely beautiful. They ran out of water. Okay, they were saved by about a month and a half. Okay, there was a deadline at which they said this is crisis, people will start dying. Okay, they had already started rationing water. You were not allowed to flush toilets, you were not allowed to do this and that, all kinds of stuff like that. Okay, and the kids see this, and they, oh my God, it's really, can this happen in my home as well? It really hits home. So the first part of each unit is showing examples of what happens when you run out of water, and showing that this is a global phenomena, okay, and zooming in what's happening locally, okay, and then we start talking about science. And so in this way, it's very clear to the kids the value of the science behind it. They understand the problem. They have no idea what needs to be done or what causes the problem. Why wasn't this problem existing? So the need to introduce the science is very apparent. Nobody, not once has a kid raised his hand and say, why are we learning this? That's something that has not occurred, okay? So the second one focuses on the science. The third part focuses on the solutions, potential solutions to the problem. And these are both engineering and scientific, future technologies, okay, and economical, and political, social, all kinds of things. They're all, there's not one solution that will solve any one of these. There's multiple different things that you have to do. And the idea is that the kids have to come up with plans at the personal, family, school, and town level, things that can be done. So we're trying to encourage, again, as I said, informed agency inside there. So that's why we went there. Okay? Now, I'm not saying that Migration Blues is not fantastic. It's amazing, okay? I'm not as confident that we will be able to hook the kids as much of that as we can with this. And I said we have also included more science fiction topics like a voyage to Mars. And I think that's what, we've included personalized medicine inside there. Okay? Which again.
Yeah, I mean, you're hitting all the Twitter hits, right? You know,
But I'm not saying, this clearly does not represent what the scientific enterprise is about. Absolutely it doesn't, okay? But this is what will get the kids on board at this stage.
Let's take one more question. I think, did Barbara have another question?
But if there's someone else, I'll come back to Barbara afterwards. If not, then Barbara.
There was someone back there, that's what I saw. But if not, it's time to go anyway, so.
Huh?
Is there one more question back there? I can't remember.
I raised my hand, but that.
Okay, fine. We have time for one more?
No, but if Joe wanted to go, my question sort of was a follow-up to Bob's question. First, I wanted to say thank you. And my issue is really deep, even one level deeper. I was wondering on these questions of self-efficacy, mastery.
I'm sorry, my
On
hearing is.
on the questions of self-efficacy, mastery, and the third component, how are you measuring them, operationalizing them, doing them in the context of the curriculum? So that kind of was what I was interested in. And so,
It goes beyond what the
that's what I realized, and I thought, well, maybe if you could give us, even one on this question about self-efficacy, but I think by describing that this issue of personal things that have to be done, which is, to me, a lot that has to do with these questions about self-efficacy and also then carry over into mastery and the rest idea. So anyway, it was really more of a follow-up to where I was going even deeper than Bob. So anyway, thank you.
Thank you very much.
All right, well, let's get to I want to thank everybody for coming. I don't remember who our next speaker is. Sue, do you remember?
We're still trying to figure it out. Oh, actually, Himio from TE, Himio Dominguez.
Well, stay tuned for postings about who our next speaker is. We'll have them come up and thank Sue for arranging all this. So, David, thank you. Sue, thank you. Thank you very much.